To begin this discussion of antidifferentiation by substitution, we're going to begin with the chain rule because we use this method for reversing a chain rule derivative. So if you remember finding a chain rule with a derivative, we are going to look at this as a composite function, and we have this outside exponent and this inside function. So to take the derivative here, we will begin by first taking the derivative using the power. Bring the power to the front, leave the inside alone, reduce the power by 1, and then take the derivative of the inside. And then what we have as our derivative is 3 times x plus 1 squared. Now, since an integral is a derivative in reverse, we are going to go backwards with this. But to do that, I'm going to give you the rule for the power formula. So the power formula for substitution, we look at this inside portion, and we're going to call this the inside portion u and make a substitution. So we will have the integral of u to the n du. Now u is a function of x. So it's actually going to be like a u of x formula, such as x plus 1. And what we do is, just like the antiderivatives that we have been doing, the simple ones, you raise the power by 1, divide by the new exponent, and then add c because this is an indefinite integral. So we're going to take this derivative that we just completed and go backwards with this. So our first step is to identify what is inside, and something that is inside of parentheses, under a radical, in a square root, in a trig function, in a denominator, some sort of group. So we're going to start by identifying the u, and the u is inside this parentheses. And then we're going to take the derivative, because we're, in addition to replacing x plus 1, we are also going to be replacing the derivative dx. So we take the derivative, and that's just 1. But what we want to do is separate the u's and the x's, so we're going to multiply the dx over. So in this case, we have du is equal to dx. So to make us our substitution, we've got x plus 1. Well, x plus 1 is u. So that is what we're going to write instead of x plus 1. We're going to put u, and it's squared. And then the next thing we're going to replace is the derivative portion of it. Now this dx right here is also right here. Dx is du. So instead of dx, we're going to write du. Now if you notice, the only thing that has not been replaced is 3. And we still need that 3 as part of the equation. So we're just going to bring that down. And so now we can take our antiderivative. So we're going to add 1 to our exponent, divide by the new exponent. We're going to add c, and the 3's cancel. And so we have u cubed plus c. But our equation started with x's, not with u's. So we're going to replace the u, or the x plus 1, cube it, and that is our answer. That's the antiderivative with substitution. Okay, for example 1, I want to find the antiderivative of this, and we have to look at how do we pick what is the inside function and what is the outside function. How do we pick u? Because we've got 2 sets of parentheses. Well, the key to this is the exponent. This one has an exponent of 3. This one doesn't have an exponent at all. So we're going to pick the inside part of this parentheses. That's going to be u. And so I'm going to start with let u equal 3x cubed minus 2x squared plus 3. And we need to take a derivative. So we'll do du dx, because we replace the function and we replace the derivative, and take its derivative. And so we've got 9x squared minus 4x. Well, if you take a look at this, we see this somewhere in our original equation. This 9x squared minus 4x matches this, so we can see that's going to be our derivative part. So I want to rewrite the derivative by multiplying the whole thing by dx. This matches this, so we're going to make two substitutions, the u and the du. So back to the problem. Y is equal to. Only thing that's not being replaced is the 4 up front, and that's okay. With anything we can't replace, we're just going to bring along. So the parentheses that's raised to a 3, that is u. The 9x squared minus 4x dx is du. And from here we take our antiderivative. So we raise our exponent by 1, divide by the new exponent, add c, but we want x's, not u's. We're also going to cancel these 4's. And you will have 3x cubed minus 2x squared plus 3 to the 4th power plus c. If you take the derivative of this, you can check it, and you're going to get exactly what we began with at the beginning of the problem. Okay, let's try one now that has a trig function. If you see now, the 4x is inside the cosine, so that is going to be the u part. So here's u. I'm going to set this aside and say u is equal to 4x. And instead of writing du over dx, I'm just going to shortcut it and multiply the dx to the other side. So the derivative of 4x is 4, multiplied both sides by dx, and we have 4dx. And you can see we've got 4dx here, a 4, and a dx there. So that is going to be replaced with du. The only thing that's not being replaced is cosine. It's going to stay in the problem. So we will have cosine u du, and there's a chart in the book on page 332 that has all of the antiderivatives of the trig functions. And so the antiderivative of cosine is sine. Add a c. Last step, replace the u. U is equal to 4x, we identified earlier. And that's your antiderivative. Now this problem looks like you have a 3-layer composite function, but you don't. If you check your chart in the book, secant squared is the result of the derivative of a trig function, and I'm going to leave that for you to look up. But what I would like you to do at this point is stop the video, try the problem yourself, and then you can restart the video for the solution. Alright, here's the solution. This one has a little change here. What you're going to notice is that when you take the derivative of u, you get a 3dx. But there's no 3 anywhere in your original derivative except where the u is with the 3x. So you don't have a 3dx. But you do have just a plain dx. And if you divide your original derivative du by 3 on both sides, you're going to have dx. Well, dx and dx are the same, and dx is 1/3 du. So we're going to put that in instead. So as long as it's algebraically correct, you can manipulate that derivative to make it look like you need it to look. So we'll substitute dx with 1/3 du, and that's why there's a 1/3 here and a du there. And secant squared is the derivative of tangent. Okay, so let's work through this one. I have a 4x on the outside. I have a 2x squared plus 1 under a radical. So what you choose as your inside is anything that's in a parentheses, under a radical, in a denominator. This one is under a radical. Here is u. So if that's u, the derivative of 2x squared plus 1 is 4x dx. Okay, so we have a match, 4x dx, right there, right there. That's going to be the du. So let's make our substitution. Y equals the square root of u du. So we've simplified this a good bit. Now, in order to take this antiderivative, you need to give that radical an exponent. It's 1/2, and that kind of looks like a y over 2, so let's fix that. That's better. Okay, now, when we raise our exponent by 1, 1/2 plus 1 is 3/2. Divide by 3/2 is the same as multiplying by 2/3 plus c. And then we will finish this problem by replacing the u with 2x squared plus 1. And in these situations, I will allow you to keep your u inside a rational exponent instead of returning it to the radical. So far, all of our antiderivatives with substitution have been with indefinite integrals that did not have numbers on our integral. We didn't have an interval, but now this one has an interval. We were going to do an additional step in the beginning. When we find u, we are also going to recognize that this u is actually a u of x. It's a function of x. We are also going to replace a, which is 1, right there, with a function. So with u of a, we're also going to replace that value by substituting the 1 into our u, and we're going to replace b with u of b. So, but then we don't have to replace the x's because we're going for a numerical value. So we're going to make a little adjustment here. So our u here is x minus 1, du, simply dx. But we also need to replace the a and the b. So we're going to say u of 1, which replaces the a, is equal to, we're going to just plug it into u, x minus 1, so 1 minus 1 equals 0. And we're also going to replace the b by plugging b into my u of x. And then we'll have 5 minus 1, and that's 4. So instead of going from 1 to 5, we're going to go from 0 to 4. So let's make our substitution. So 0, 4, square root of u du. And we're just going to take the antiderivative like we did before. So this is 2/3 u to the 3/2, and we're going to evaluate this from 0 to 4. Because we replaced the 0 and the 4, or the 1 and the 5 with a 0 and a 4, we don't need to replace the u back with an x plus 1 because we changed everything. So we add a step in the beginning and take a step off at the end. So we've got 2/3 4 to the 3/2 minus 2/3 times 0 to the 3/2. Now a 3/2 exponent simply means we're going to take the square root and then cube it. So Square root of 4 is 2. 2 cubed is 8. All of this is 0, and we just simplify with a 16 over 3. Now, this is not an area problem. We're just evaluating an integral. We're going to get into area again later. So if you get a negative, that's also okay. Okay, this is the last example, and it is going to be with a trig function. It's a definite integral, so when we replace our u and our du, we're also going to replace a and b with u values. So the 2x, that's on the inside. So u is 2x. And that means du is 2dx. But let's look at the original problem. I only have a dx. I don't have a 2. So I am going to divide the derivative by 2 on both sides. So that gives me 1/2 du equals dx. So it's the 1/2 du that's going to go in the problem. I also need to find a new a and a new b. So I'm going to have u of 0, which means, and u is 2, so 2 times 0 equals 2. And then I'm going to have u of pi over 2, and that's 2 times pi over 2. And so that's just pi. And sorry, that was a 0 right there. So let's make our substitution. So from 0 to pi, we're replacing 2x with u. We're replacing dx with 1/2 du. And then we take our antiderivative. Now, to get a sign in a derivative, you have to take the derivative of negative cosine. So when the sign changes, you have to take that into account. So we have a negative 1/2 cosine u, and this is going to go from 0 to pi over 2. So we're just going to substitute. Negative 1/2 cosine pi over 2 minus a negative 1/2, so that's going to be a plus cosine of 0. So we got negative 1/2. Now cosine of pi over 2 is negative 1, I think. Wait, this is not a pi over 2. This is just pi. Let's fix that, and that's right there. Pi, pi. Okay, cosine of pi is negative 1. Cosine of 0 is positive 1. So we have a 1/2 plus a 1/2, so it's just 1.